your side? Yeah, we're good. Cool. Awesome. Hey, welcome everyone. We'll get started. Yeah, so welcome to yet another Dublin Island Scala user group meetup. So for people who are new, we meet about every month-ish to usually, talk about Scala and chit-chat. If you're interested in giving a talk, we have a website up with a contact form, so if you want to give a talk like this, feel free to reach out either via the website or talk to any of us organizer. We'll be hanging around afterwards, and we're always welcoming kind of new speakers, because that's the point of local user groups, right? After the talk, as I said, so feel free to hang around. There's going to be beers and pizza. The Wi-Fi password is up there in case you need it. So there's a guest Wi-Fi with the password. A few other boring stuff to get through. Yeah, so the toilets are up there on your right if you need to. Help yourself to beers and soda if you need to. Has everyone signed in the attendance sheet that's up there? Yes, if you haven't, please do so. So there's still time to run up there and go and sign it if you haven't. We won't mind. Yes, thank you. Apart from that, yes, last of the boring stuff. Yes, fire exit. In unlikely event of a fire, which we do not wish, so please be careful. We have your names, so don't start the fire. Also, the fire exit is the way you entered. So same way out. You should be able to find it. Finally, a big thanks to Zalando for hosting us. We are hiring, so if you're interested in jobs, we are looking for Scala programmers. So just check out tech.zalando.com/jobs. And that's it for me. Without further ado, let's give it for John and Kai, who are going to talk about error management and ZIO versus future.
Thank you. Thank you for that introduction. And I want to thank Zalando. Wow, I'm loud. I want to thank Zalando for hosting this meetup on a Saturday of all days. I know that's not easy to make happen. And then the Dublin Scala user group meetup for making this happen on such short notice. And thank you all for giving up a couple hours of your weekend time to come out here and listen to me and Kai talk about ZIO. So ZIO is a library for concurrent and asynchronous programming. And one of the biggest challenges, in my opinion, about modern application development is actually error management. Error management is a bit of an architectural nightmare in modern apps. And part of the reason for that is error management is complicated by the fact that today's applications are asynchronous. So we've got all these callbacks going on, we've got jumps to thread pools and so forth. And that leads to a lot of problems. And then not only are today's applications asynchronous, but they're also concurrent. So they're spinning up lots of threads or lots of futures, doing lots of stuff in parallel. And all this adds tremendous complication to error management. And as a result, we see lots of architectural anti-patterns. And like I said before, I work on ZIO, a library for concurrent asynchronous programming, that tries to take a fresh look at a lot of the problems in error management. A fresh look with the eyes of a functional programmer and with a more sort of mathematical mindset. So today I am super excited to talk to you about functional error management using ZIO. And what I'm going to do today is I'm going to contrast functional error management with ZIO with sort of procedural error management using Scala's future. How many people have used future in their code base? So almost everyone, that's great. How many people have used ZIO? How about Cat.io? Oh, nice. Harmonix? Okay, great. So that's good background. I think that's enough to understand what I'm doing here and what we're going for. So what I'm going to do is I'll compare and contrast error management with future with ZIO. And then in part 2, I'm going to let my co-contributor Kai take over, and he's going to talk about a newly added feature to ZIO. There's not even a pull request for it. It's brand new. So we'll do a pull request today or tomorrow. But this is a new feature in ZIO that will revolutionize the way you look at debugging asynchronous and concurrent code. You're going to be amazed. At least I was amazed. and to help me do that and introduce part 2 of this presentation today is going to be a friend of mine and co-contributor of ZIO, Kai, who's worked with me on the project for, I think, 9 months, almost a year. And he's one of the rare people who started out in Haskell. And he defected to Scala. Why? Well, because Scala allows you to do pure functional programming, but it also has modules, which is something that Haskell doesn't have. And Scala does an extraordinarily good job at handling modules. So it's been a pleasure to work with an ex-Haskell defectee, Kai, who's worked on a number of really cool features in ZIO, and who also happens to be one of the most brilliant people I know, just super smart, and I'm always excited to hear his perspective. He always has a different perspective, and he always makes me think about tough design decisions in ZIO. And he's worked extraordinarily hard on this feature, which is sponsored by Septimal Minds, for many, many months now. I know this has been in development for quite some time. So I'm really excited that we're able to show this here with you today, and I would like you to help me welcome Kai and also thank him and Septimal Mind for all the awesome work that's gone into this feature. So please join me.
Today I will show you how ZIO can revolutionize error management and diagnostics for concurrent and asynchronous applications in Scala. You will not want to write anything new in anything other than ZIO, or at least you wouldn't run it on anything else than ZIO runtime. I guarantee that.
Thank you, Kai. I'm going to briefly introduce Future and ZIO, since ZIO is fairly new. Not a lot of people have experience with it. I'm going to contrast it with Future so you can understand how it differs from the Future baked into Scala. And then I'll talk a bit about managing errors. Like, what are some of the hard problems, and what are some of the design choices where Future went one way and ZIO went a different way? And then Kai's going to take over and talk about next generation debugging. What do you do when things go wrong? And what are some features that can help you quickly narrow in on the problem and fix it without a lot of time or extra effort or print lines or logging lines? And then finally, we'll wrap up with a brief conclusion. A tale of two effects, Future and ZIO. So Future is baked into Scala, and its defining features are, number one, the ability to model asynchronous computations. So Future solves callback hell. You've ever dealt with callbacks, they're nasty. Future gets rid of that problem in a very nice fashion. Future can also parallelize code. Every time you create a new Future, it's running in parallel. It's very easy to make parallel code with Future. Future also bakes in its own error channel. And finally, possibly the most defining characteristic of Future is the fact that it's eager. So if you have a Future, it represents a handle on a computation that's already running. ZIO, on the other hand, is radically different than Future. So Future represents a computation that's running, a side-affecting computation that's running. This is not a functional way to program, it's a procedural way to program. In procedural programs, you program with side effects, things that do things. ZIO, on the other hand, is a functional way to program. Instead of doing things, it describes things. So the core type in ZIO actually doesn't do anything. It doesn't represent a handle on a running computation. It is nothing more than an immutable data structure. Just like list or option or anything else that you're familiar with, it's an immutable data structure that describes interaction with the external world. Things like reading from databases and reading from configuration files and running things in parallel. And as a result, it is a purely functional construct. In procedural code, we write our programs using statements, and these statements are recipes. We first print a line, and then we read a line, and then we print another line, and then we return some value. This is a collection of statements. Side-effecting statements. The execution of each statement is associated with interaction with the real world. In the case of ZIO, on the other hand, we never actually interact with the real world. We just take immutable values and we call methods on them to produce other immutable values, like all the methods on list. So on the right-hand side, you can see how we would create a description of the same program that's modeled in a procedural style on the left-hand side. The program on the right-hand side doesn't actually do anything. It just composes together a bunch of descriptions using flat map, flat map, flat map, flat map, and then a final map at the end of that for comprehension until it builds a single effect that models the entire sequence of instructions. ZIO effects can be thought of as trees, immutable trees, where every node in the tree represents a description of an operation to perform at some point in the future. So on the left-hand side, we have a collection of statements, side-effecting statements. On the right-hand side, we have a purely functional value that has no effects. Now, I'll admit, what's on the right-hand side is written using for comprehension. And that doesn't look exactly like a bunch of statements. And this style of programming has to be learned. It doesn't come naturally. You have to learn about for comprehensions and flat map and all that stuff. But it can be learned, and it doesn't take too long. And once you learn to program in that style, you can benefit from all the features in functional programming libraries like ZIO and ZIO and Monix and so forth. Now, you may ask, why do this? Why go through all the hassle of learning how to use for comprehensions just so we can write in a purely functional style? The answer is, it's not just so we can write in a purely functional style. We actually get a tremendous number of benefits from describing effects rather than actually doing them. Basically, we give our programs superpowers. First off, ZIO's effect type has more than 100 times the performance of Scala's future. In some cases, up to 1,000 times faster. It's tremendously faster, which matters when building real-world software. Performance matters. Not only that, but over your entire application, we get composable free timeouts and cancellations. So you can take any computation that's running anywhere, and without writing any bit of code, you can time that out, or you can cancel it. And that instantaneously interrupts it and cleans up all resources associated with that. That's tremendously powerful. If you're doing web requests, for example, you could put a 60-second timeout on the amount of time it takes to return if you wanted to in some way cap the amount of resources that went behind servicing a given web request. And you get all that for free across your entire application without writing any code. You also get something called effect combinators. So it's not possible to write a function that takes a future, for example, and returns a new future that does the thing of the first future again and again and again until it succeeds. That would be a future combinator, a function that takes a future and returns another future. It's not possible to write that. Why? Because if you have a future, if you have a reference to a future, that computation is already running. There's no restart method on future. However, when you're dealing with the realm of pure values, like ZIO effects, you can write effect combinators. You can write a function that takes an effect and returns another effect that represents doing the first one many, many, many times until it succeeds. So this enables whole new ways of programming. It opens up the door to writing program combinators, functions that take programs and return programs. You also get the unprecedented ability to have a version of try finally in your application that works across asynchronous regions and concurrent regions. This is the try finally you know and love, or maybe you know and hate from Scala and Java, except it works and it doesn't lose errors in any case. And this is something that Future doesn't have. So it's very hard to write applications that don't leak resources with Future because they don't have try finally in there. Whereas that's baked into ZIO and it has the same guarantees, actually stronger guarantees than the guarantees you'll find in Scala or Java. ZIO has a fiber-based concurrency model, which allows you to execute 100,000 or 1,000,000 different effects simultaneously without blocking on a finite small number of threads, for example, 4 threads. in a very high performance fashion. That's, like I mentioned before, already way more performant than future. And based on this fiber-based concurrency model is other powerful things like lock-free, interruptible, asynchronous concurrent structures, like a ring buffer that's super fast and back-pressured on both ends, or software transactional memory that lets you do declarative concurrency without any locks or race conditions and with full ability to cancel any in-progress computation. Of course, the main benefit that you probably already know about from functional effect systems like ZIO is the fact that they are purely functional, and that gives you something called equational reasoning. That lets you refactor your code safely without changing its meaning. That's not true of future-based code or statements. You can't just pull out a bunch of statements and stick them in a variable and not change the meaning of your program. That will change the meaning of your program. Basic refactoring operations that you do on the rest of your code don't apply to effectful code, but because ZIO doesn't involve any side effects, you can use all refactorings everywhere over your entire code base and have the guarantee that you're not going to change the meaning of your program. And use of functional effects pushes a lot of information into types. So you can look at a type signature. You can know more about what that does. You can't look at a function from any unit and know anything about what that does. But you can look at a function that goes from a string to a ZIO effect that fails in a certain way and uses a certain number of environmental effects, and you can know more or less precisely what that does just by looking at the type. ZIO has very strong support for testability. Baked in, out of the box, you can test anything. Anything in ZIO that looks like it's actually interacting with the real world is not. And you can test that out in fast, deterministic unit tests. And not just in ZIO, but in your own code. And then finally, what we're going to look at today is error management and debugging. So what does that look like? What does it look like in future? And what does it look like in ZIO? How do the two stack up against each other? And is there a compelling reason to use ZIO just so you can solve the major problem that is error management in today's asynchronous and concurrent applications? So let's quickly review the core type in ZIO, and then we're going to jump right into error management. The core type in ZIO is the key to understanding the library. You get this, and nothing else you see in the library will be confusing. The core effect type is called ZIO, and it has 3 type parameters. This ZIO effect type is an immutable data structure. It's an ordinary value, and it represents an effect. It describes, as a data structure, some interaction with the external world. The meaning of the type parameters is as follows. First off, R is what the effect requires in order to be run. So different effects might require different things. For example, one effect might require some configuration information. Another effect might require access to a database. Another one might require access to some sort of business API. Another one might require access to Spark context. The E-type parameter is the type of values with which the effect can fail. So obviously a lot of effects will fail because of throwable, but some might fail because of IO exception, or some might fail because of some business-specific domain error inside your application. And some might fail with a value of type nothing, which means they don't fail at all, because nothing is the magical type in Scala that has no inhabitants. There are no values of type nothing. So if you see nothing plugged into that type parameter, it just means that effect can't fail. And then finally, A is the type that if the effect succeeds, it will succeed with the value of that type. And that corresponds to the A in future. So a future of A and the A here in this ZIO effect have the same meaning. And same for cat's IO or Monix task or other things. That's the A in those different effect types. And even though this is not really precise, this can be a useful way to think about a ZIO effect as a function from R to either E or A. So in order to run this ZIO effect, you need to give it an R. You need to give it the R, which is the thing that it needs. And then you're either going to get back, if it fails, you'll get back an E. But if it succeeds, you'll get back an A. Now, you don't always need all these type parameters. So to handle the 4 common cases there are some type aliases in ZIO to make this more beginner friendly. And these type aliases also have companion objects. So you can call all these methods in the companion objects and use these type aliases and pretend that the type parameters you don't want don't even exist. So type task of A represents a ZIO effect that has no requirements. It doesn't require anything from its environment. You could feed it anything because it doesn't require anything. You could feed it a string or an int or whatever. It doesn't need anything, so it doesn't matter. It's not going to care what you feed it. And it can fail with a throwable or produce a value of type A. UIO, that stands for unexceptional. And that represents a ZIO effect that doesn't need anything, can't fail, and can succeed with a value of type A. Task R represents an effect that needs an R. So it needs an R, you need to give it an R in order to run it. It can fail with any throwable, and it can succeed with a value of type A. This is the type, if you're using CATS effect libraries, this is the type that's most useful. You're probably going to end up using this. And then finally, IO of EA represents an effect that doesn't need anything and can fail with an E or succeed with an A. One of the most powerful features of ZIO, but also sort of day-to-day and very practical, is the fact that you can take synchronous code and you can lift it up into ZIO. You can take async code and you can lift it up into ZIO. You can take lots of error code, whether it's from eithers or options or futures or whatever, and you can lift that up into ZIO. And then you can take lots of resource-related effects and you can lift that up into ZIO, allowing you to take all these different things, which are different models of computing, really. Synchronous computing is different than asynchronous computing, and it's different than errorful computing, and it's different than resourceful computing. All these are different modes of computation. You can take all of these different things and you can lift them up into ZIO, allowing you to program with a uniform fabric across the entire structure of your application. So some of your methods return either, lift them up into ZIO. Some of them return future, some of them are ordinary synchronous code, some of them are doing the equivalent of try finally and so forth. You can collect them all up and you can model all of your program's effects in a uniform way, which is tremendously simplifying. And also, as we're going to see, can tremendously help with error management. Because when you program in different styles in different parts of your application, because you're doing async or resource stuff or concurrent stuff, when you program in different styles, you're responsible for error propagation. And that means it's probably not going to happen. It's just too painful. We'll see what that looks like later. Error management. So in this section, I'll look at how does future allow us to manage errors, and how is that different than ZIO? And in every single case, we're going to see that ZIO provides more facilities to manage errors than future. A lot of application architecture becomes simpler when we recognize that there's not just one type of error inside our application. There's actually two distinct categories of errors. And these are expected errors. These are the ones we expect to happen. You know, there's some sort of user story that talks about them. They're domain errors, they're business errors, they're transient errors. These are things we know are going to happen. We know about them, and we know what we're going to do in case we get them. We know we're going to retry, or we're going to show a message to the user, or we're going to do something like that. And then in the other category, there are unexpected errors. These are things like Stack Overflow exceptions, or the database just stopped working, it locked up, it seg-faulted. Or defects in our code, which of course we have no way of knowing about, otherwise we fix them. And these are the things we don't expect to happen. Of course, we know they're going to happen, right? We know there's a category of things that we're not going to expect and plan for that are actually going to bring down our production application and have us up at 2 a.m. in the morning trying to figure out what went wrong and fix it. But we don't expect to handle them. And it's a best practice in a statically typed language to separate these two using the type system. So what we do is for all the expected errors, ideally, we reflect those errors in the types of our application. Why? Because we expect them and we want to handle them, and therefore we want the help of the Scala compiler to carrot us along into handling them. We want to make sure the Scala compiler is our friend, helping us handle the errors that we expected and that we knew we wanted to handle. On the other hand, unexpected errors, not only is there no way really we could represent them in types because we don't know what they're going to be, but also there would be no value to doing that because they're unexpected errors. We don't know what to do with them. If we don't know what went wrong, we have no idea how to handle that. The best you can do with an unexpected error is sandbox it to limit the damage that it does to the overall application. And there are certain key points in every application where you know when to sandbox. For example, doing a request. If you're satisfying a request, you can sandbox that. And worst case, shuts down the connection of the client who called that. So this is best practice. We handle expected errors with the aid of the Scala compiler by pushing them into the type system. And we handle unexpected errors by not reflecting them in the type system because there's no way we could do it and it wouldn't provide any value if we could. We just, at best, sandbox that to some area, well-defined area of the application. Now, Future actually does have this sort of error duality baked in, but it doesn't follow best practices. You see, Future has a baked-in error channel that's fixed to throwable. And it uses that same error channel for both expected errors and unexpected errors. And the only way you can tell the two apart is that the unexpected errors are wrapped in something called execution exception, which is a gotcha for Future programming. You've probably caught something and you were surprised to discover this thing called execution exception because your code would never throw such a thing. It was Future trying to wrap that and trying to basically hijack that primary error channel for also talking about and giving you a way to deal with the side channel errors, the unexpected errors in your application. But because these errors are not part of the Future type, that means you have no compiler assistance for helping you deal with the class of errors that you expect. Whereas in ZIO, there's this error type parameter called E. And this error type parameter is for modeling all the expected errors in your application. So for ZIO, expected errors are reflected in the type of the ZIO effect, whereas unexpected errors are not so reflected. And that's the distinction. That's the best practice distinction that Scala is capable of enforcing and that ZIO leverages to help you write better code whose error properties you can reason about. You can look at a ZIO effect and you can know if and how it's supposed to fail. And the compiler will help you deal with the errors that you're supposed to. A really interesting thing happens when you take a data type and you add the ability to add finalizers to it or the ability to do stuff in parallel. And that interesting thing is you run into situations where your code out there executing in the wild is going to produce more than one error. And the following example shows you what this looks like. Let's say we have a bit of code that forks off into two branches. So we've got two things running in parallel. And let's say the first branch fails with an error of type E1. And then let's say the second branch, which is out there executing in parallel, it fails with an error of E2. And let's say further, just to make this as interesting as I possibly can, let's say that second branch has installed a finalizer. And that finalizer is broken, it's defective. And so it's going to throw some sort of unexpected error as it's trying to clean up some resources. So we've got E1, we've got E2, and we've got T. We've got three errors all initiated from a single point in the code. What's going to happen here? Three errors, but error channels typically only allow you to handle one error. Well, it's interesting to look at what Future does. So Future throws away all parallel errors, except for one. It's going to pick one of the parallel errors and it's going to give you that one. And the rest of them are gone forever. And then the error in the finalizer, you don't have access to that. It's actually reported in a side channel, in the execution context associated with the execution of whatever code triggered that. It'll be a call to report error on that execution context. You don't have access to that. You can't handle it. You can't recover from it. You don't have knowledge of that. You can choose to log it or dump it off on something on the side, but that's it. What about ZIO? Well, ZIO uses a structure from functional programming called a semi-ring. And a really cool thing about semi-rings is, well, free semi-rings, is that they allow you to take a base type E that represents your error type and then capture sequential and parallel composition of these errors in a lossless fashion, 100% lossless. And that's what the cause data structure in ZIO is. So even though, for the most part, when you're interacting with the surface of ZIO, you deal with E's, anytime you want, you can access this rich, free semi-ring structure that gives you total access to all parallel and sequential errors in your codebase. And how this cause-free semi-ring enables you to capture, or rather is used by ZIO to capture all errors, is quite simple. So in this example, cause fail is used to capture E1, and then cause both is used to, well, cause fail is used to capture E2, and then cause both is used to capture the parallel failure of both E1 and E2. And remember, right after E1 or E2 failed, the finalizer failed on the way out, so that's sequential error right after E2. So then the cause then constructor is used to capture the fact that E2 happened before T on the same parallel branch. So now we have a total lossless description of everything that went wrong in the system that's accessible to user land code. And not only that, but if you see one of these things in a log file, you can visually see the structure of that error. You can see what happened in parallel and what happened sequentially just by looking at it, and it contains full information. Another interesting aspect of error management is error propagation that I alluded to earlier on. Error propagation is something that we have to do manually in ordinary code. So we have some actor stuff over here, and we have some future code over here that does maybe web API calls and stuff. And we have some synchronous code that talks to JDBC, and some resource-related code that's loading from files and cleaning up after them and so forth. And best practice is actually to propagate errors through the different subsystems. So if one piece of the code initiates an action that trickles over into the actor subsystem and then into a future subsystem, and then over here into this subsystem and so forth, we're propagating errors basically in reverse order in a lossless fashion. Now, this does not come for free. If you write your own code, then you have to do this manually, which is why it's just not done. It's too hard. It's too unreasonable to expect people to do this. Future provides us a little bit of help because it propagates errors in asynchronous sections. So if you have two async regions, for example, that are chained together using Future's flat map, then an error in one will propagate to the outer one, so you'll be able to locally deal with and reason that error, even though it consisted of potentially any number of different independent asynchronous regions. However, when it comes, Future doesn't really allow us to model resource effects or synchronous effects. And also, furthermore, even though it does allow us to model parallel and concurrent effects, as we've already seen, it loses information. It's not lossless. It actually throws away lots of errors. So it doesn't do a great job at propagating information from parallel and concurrent regions to other regions in the codebase. Whereas ZIO models all these different effect types and has automatic error propagation that is 100% lossless between all these different subsystems. So when you're using ZIO, there is no manual propagating from the actor subsystem to this subsystem to that one, to that one, to that one, to that one. It just happens automatically in a lossless fashion. Error recovery. This is obviously a very important property for any application, is the ability to respond to errors. It's what makes our applications resilient and reactive. And both ZIO and Future have facilities for responding to errors. For example, there's a fallback operator in Future that allows you to do this feature, and then if that fails, fall back and do another one. In ZIO, this is called or else. You can do this effect, or if it fails, you can do the other effect. The primary difference here, however, is or else is strongly typed. If the first effect fails, then the composed effect, that is effect 1 or else effect 2, can only fail if the second effect fails, and it will fail for the same reason. that the second effect fails. The type signature itself tells you that when you have composed any chain of A or else B or else C or else D, that the composed effect that you get out of that can only fail for D's reason, if it can fail at all. So the type system, the Scala compiler, is aware of the possibilities of failure and is telling you what can and cannot happen. That's tremendous. When you're trying to reason about the error behavior of your code, this is a tremendous advantage. And fallback, you can call that as many times as you want, and because that error is dynamic and baked into future, it's never going to go away, it's never going to change, and you're always going to have to deal with that possibility of failure. Both ZIO and future have means to catch errors and recover from them, and the primary difference here, again, is that catch-all in ZIO, which is the equivalent of future's recover-all, makes the error type disappear. If you handle all errors, you get back an effect type that has an E equal to nothing. You and the Scala compiler know that you handled all errors, whereas the effect of future doesn't change because the error is not reflected in its type signature. And then if you don't want to deal with all errors, well, you can always use catch sum. ZIO also has handy fold methods. So like option has fold, and either has fold. Lots of data structures in Scala have fold. ZIO has a fold that allows you to handle error and success at the same time, both as pure values and also effectively with the fold M variant, which can make for some very compact code. And then finally, ZIO has facilities that future does not have for taking that error channel information and bundling it up into a value. So for example, you can eliminate the error by turning that error channel into an either of EA or into an option of A if you don't care about the error type. A very simple, compact means of getting rid of your error type and bringing it to the value level where you can operate over it, flat map over it, and respond to it in that fashion. And then the other really powerful method it has is run. And run, what run does on an effect is it captures all the information about what happened when that thing was run. And it puts it into a data structure called exit. And exit will contain the full cause if there was failure information. Parallel, sequential, all that stuff is there. So you can see, basically sandbox it and see what went wrong. Did it blow up because of a defect? What really went wrong when this thing was run? And that allows you to sandbox parts of your code where there are unexpected errors. You can't recover from them, but you can sandbox them. ZIO's effect capabilities are quite different. Not even Haskell has them. And as a result, it can be a little confusing. If you start using ZIO, there are lots of questions. How do you use these capabilities to build applications? What's proven and what's not proven? And obviously ZIO is a fairly young library. It's very new. It's newer than everything else out there. So we're still discovering some things, but I think it's been in production for long enough that we're gaining some feel for how we use these capabilities to build robust, principled applications. And so I'm going to share with you 4 tips today. If you want to give ZIO a spin in your application, then these 4 tips will help you build solid, principled code that follows currently known best practices. Not saying it can't be done better, but this is the best way we know how today to build resilient reactive applications using ZIO. Number 1, don't type unexpected errors. It can be a bit tempting when you first discover typed errors to try to stick everything into the error type. That's a mistake. And the reason why that's a mistake is because you cannot recover from many types of errors. What are you going to do if the database seg faults, for example, or if there's a Stack Overflow exception or something? You can't do anything in those cases. Let it die. Let it crash is the Erlang philosophy. And that's a good philosophy for all unexpected errors. Sandbox it, but let it crash. And a facility in ZIO, a method on the ZIO effect called refine or die lets you do that. So if you have an effect that fails for some throwable, for example, you can pick out certain recoverable errors out of that. And you can just let the rest of them kill the fiber that's running that effect. And in this example, calling refine or die on this thing, which started out with error type throwable, allows us to refine it to have an error type of temporarily unavailable. So this is the only one we care about. And the rest of them are just going to have it crash. This is the only one that we care about that we're going to reflect in the error type, because it's the only one that we expect and that we know how to recover from. Number 2, do extend exception with sealed traits. So sealed traits allows us to, if we have a part of our application, a little module of our application, then we can say that all methods in this module fail for a certain reason. Namely, in this case, it's a user service error. And then we can seal that trait, and we can extend it by, in this example, 2 cases, invalid user ID and expired auth. And what this allows us to do is if we have a reference to a user service error, we can match against it, and the Scala compiler knows there are only 2 possibilities. Why? Because it's sealed. This is a sum type. This is an enumeration. The Scala compiler knows only 2 of these things exist. If we don't match on all of them, it's going to warn us. Actually, it'll be an error. It'll say, hey, you need to make your match exhaustive if you've turned on the fatal warning for that. And that's a good thing. We want to be able to handle expected errors that we know how to recover from. So sealing these traits gives us great power. However, we also want to extend, we want all of our errors to extend a common supertype. Why? Well, let's say we have this for comprehension here that calls the user auth function, and it can fail with expired auth. And then another one we call user profile, it can fail with invalid user ID. And then let's say we call generate email, and that can't fail at all. And then we call send email, which can fail with email delivery error. So we've got a lot of different errors here. A lot of different these individual methods can fail in different ways. And what happens when we extend a common supertype is that the flat map method in ZIO's effect auto widens the error type to the most specific error type possible. So in this particular case, the most specific error type is going to be exception. So the inferred type of this for comprehension will end up being exception, which gives us as best information as we could hope to get out of this. We've lost information on the particularities of it. We no longer know which of these error types it is, but we know it's some type of exception, which is more information than nothing. And then in Scala 3 introduces an exciting new feature called union types that is going to enable us to have even more precise information and remove the requirement to extend some sort of common error type like exception or throwable. But until then, use sealed traits that extend either exception or throwable, and you'll get the benefit of specific errors in parts of your application where you know about them, but then you'll get the ability to auto-widen to the deepest common supertype of a bunch of different calls to different systems in your applications. And you don't have to write any boilerplate. Scala infers this automatically without any pain. ZIO is a fully inferred type, or fully inferred library. There's no need to add type annotations to anything. Number 3, don't reflexively log errors. It can be very tempting to log errors when they happen. And it's interesting to understand the sort of psychology that goes into that. Ordinarily, when programming in modern async concurrent applications that have all these different subsystems, and in which we're not propagating errors, and in which try finally loses errors, and future loses errors, ZIO loses errors, all these different systems out there that lose errors, our reaction to that is to program defensively. If we got an error, we better log it, because otherwise it might go away, and we're not going to figure out what went wrong. But when we're programming with an effect type that allows us to never lose any errors, even if we don't handle any errors, it's still going to be sent to an unhandled error thing that you can set up when you run your effect. There's no way to lose any errors, and the errors propagate automatically through all the different subsystems in our application, which means we don't have to be fearful anymore. We can rely on higher level code to handle it, or if it doesn't, it'll be passed off to something that does. And that gives us the ability to log less. Logging less is a good thing. There's too many errors, useless random errors, cluttering up log files that were recovered from at some point in an application that just add noise. They don't really help you understand anything. So trust the code above you to handle it. Your errors are reflected in the types, they can't be lost, and they will be handled somewhere. So trust that, and don't log reflexively. And finally, number 4, do get to know unexceptional I/O. And that is any case where the E is equal to nothing. And why is that powerful? Well, it give you the ability to reason about the error behavior of your code. Process upload here is a method that can fail with upload error. But the moment we call .either on that, we get back an effect that returns an either, which means this composed effect can't fail anymore. It returns an either of, upload error or the value, so that can't fail. And then, as a result, the composition of all these things together can't fail. So we know that. Scala knows that. And IntelliJ IDEA will know it too. If you, let it infer the type and you expand it out, you're going to see that the composition of all these different things can now no longer fail. And honestly, that is the biggest benefit right now of type errors, is that transitioning point between this can fail and this can't fail, knowing that you've handled errors in some sections of your code and that you have yet to handle errors in other sections of your code. So those are my recommendations for best practice. And now we're going to move on to part 2 of this presentation, in which Kai is going to introduce what he and I have been working on, that Septimal Mind sponsored, which is a killer new feature for debugging asynchronous and concurrent applications. If you've ever had to debug future-based code, you know what I'm talking about. So we're going to take a close look at what it's like to debug async and concurrent code using Future, and how that compares to ZIO using this new feature that Kai and I have been working on. So please help me welcome to the stage Kai.
Thank you for coming here. Let me tell you a short story of how we got involved in ZIO at all as a company. Back about a year ago, our stack consisted of Akka HTTP and Scalactic Core Monad. The Scalactic Core Monad is basically like a try-monad, but it allows you to accumulate failures in imperative computations. There were quite a few problems with it. The chief is that it made us work in just one error type. We could not easily change our errors, we could not easily model our errors. And the other is that with imperative computations, it's very easy to lose errors. You just forget to flat map and the error is swallowed. Because in imperative computations, the side effects still happening, you don't notice when you forget to flat map. We were very tired of the situation, and we tried to look everywhere for an error model that could suit us. We were just going to write our own error monad from scratch, but the hype reached us, and we found ZIO. We inspected it, and we thought that, well, basically that's exactly what we're trying to do. And after that, we've adopted ZIO, we started contributing to it, we've added some missing pieces, like we've added cast effect integration that we didn't have before, we've fixed some bugs, but there was always one annoying missing feature, one annoying bug that really was never solved by functional programming. One where imperative programming was just straight up better in every front, every way. But today I'm going to show you that this was fixed just forever. So let's start with a simple example involving features. Here we've got an asynchronous database call, and we've got two select queries that use that call underneath in their implementations. And what I'm wondering is, if any one of these select queries failed, what would be the debug information that we get that would help us diagnose the issue? This is the stack trace we get when a feature fails. It's a pretty long one, and it contains a lot of inner workings of the feature, but unfortunately for us, there is just one line in which any of our logic is mentioned, and it's just the asynchronous database call. And why is that? It's because every time a new feature is created, it creates a completely new stack trace, unrelated to any previous feature, and we simply don't know. We simply cannot possibly know which one of these two queries was one that produced the error. So let's throw all that out. Let's rewrite all this hideous code in ZIO. We just basically log an error string and query the database asynchronously, same as before, and we get a failure. And this is the trace we're going to get from that. This is actually two traces. One of them will show the past of the computation. What error operations executed right before the failure, and another will show the point at which we were supposed to return had the computation not failed. Let's dig a bit deeper and look at the internal representation of the for comprehension without the sugar. We've got a couple calls to flat map and map. And the green part is the past of the computation, the two operations that were executed before the database was queried. And the pink line is the one operation we were supposed to return to, the future of the computation. Does it work? Okay. So let's return back to the original example with the synchronous database call and two queries. Now we're written in shiny ZIO. This is the trace we get when a query fails. As you can see, the very first line of the future trace shows us that we were supposed to return to select humans. This is the query that actually spawned the database call. Through asynchronous boundaries, we can still trace it. And this is great. This is fantastic because we just reached feature parity with plain old Java. We can just program the way we used to program and get all the plain old debugging information. But that would be pretty boring if we couldn't go above and beyond, if functional programming couldn't do better than whatever plain Java can do. So here's another example. We've got simple Scala procedural code which calls two procedures, do main work and do side work. And had do main work failed, what we really want to know is if side work ever happened. That would really help us narrow down the possibilities and find and fix that bug if we only knew what was at stake. But unfortunately, when failure comes, there is no mention whatsoever of side work in the trace. Let's rewrite everything in ZIO again and look at the ZIO trace. The ZIO execution trace shows us all the past operations that happened before the error happened. We can see immediately that do side work happened, then do main work happened, and we just narrowed down the possibilities of failure, and we made some money, as time is money, as we saved our day from painful debugging. And this is actually the most exciting new feature. So what happens in this code is we go over a list of users or a list of pets, and we're executing upload task in parallel for all of them. If we had written this in plain old Java, that would just iterate over the list and spawn a new thread for every element of the list to upload it. If any one of those upload operations failed, the stack trace would not contain any real information. As the thread creates a new stack trace, it does not have any information about the past threads or the thread that spawned it or anything. But we just know that some upload failed somewhere, and we don't know what that upload was and what really happened. But the same code in ZIO, it gives us quite a lot more information. First, we know, of course, that the upload has failed in fiber 1. But we also now know that fiber 1 was spawned by fiber 0. And we have captured the fork point, the exact point where the fiber was created. It was in upload users. We now know that the worker fiber that failed was spawned by upload users. We can trace back, we know exactly the parallel computation that failed, and we can fix our error. The great thing is that you don't have to actually write everything in ZIO. You can still use all the tagless final libraries or the code that's written for the bad old days of ZIO. You can use it with FS2, with 2B, with HT4S. You just have to run it in ZIO, and you immediately get traces and insights into the internal of the API libraries. Whenever something fails, you can go and create a fantastic bug report that includes every detail. And the greatest thing is that the ZIO tracing is not just a toy. It's not just something you whip out when you have a small reproducible bug that you just want to find out what's happening there. We don't have time for that. We got errors in productions that are unreproducible, unknown. We must have as much information as possible exactly when it happens, because we don't know when we'll be able to reproduce it, if at all. And ZIO tracing is so fast that you can just enable it in production and not worry at all. Even with tracing enabled, ZIO is still 50 times faster than future. It's got 10 times faster than any mono transformer. And if you do actually find a spot where flatmap performance is really limiting you due to tracing, you can disable tracing for that region and regain the blazing fast ZIO performance. A year ago, when I just started using ZIO, when I just got into functional programming in Scala, I would say there were many reasons to use functional programming in Scala, to choose it. But there was one huge reason to avoid it and not do it. And I say that this reason has been undone. There are now no more reasons not to choose functional programming. Thank you.
Thank you, Kai. So there you have it. Basically, monadic stack traces that are extraordinarily detailed compared to normal stack traces, because they show you what happened inside the method. Not just the call stack, but what happened inside the method. Not only do they show you what happened inside the method, but they show you the future, what was going to happen. That's powerful. And previously to this date, like, one of the major pain points with future was debugging. One of the major pain points with all the functional effect systems was debugging. These things are not easy to debug. And now if you're doing pure FP, you have all the same benefits that you get from stack traces plus some. In other words, if debugging, diagnosing problems, and fixing them quickly is of paramount concern to your business, and it probably is, then now there's yet another reason to give a functional effect system like ZIO a try. So I want to thank Kai and Septimal Minds again for all the amazing work that went into this feature. I am super excited to try this in production as soon as this PR lands. I hope you're excited to try it as well. And I also want to invite you to, if you've not tried a functional effect system, if you've not tried ZIO or Monix or ZIO, then give one of them a try. Because these are increasingly some very powerful ways that you can write modern async and concurrent applications. And they are just jam-packed with feature after feature that gives you and the business value, saves you time, saves you money. And they're faster than future. There's basically no reason at all not to give one of these systems a try. And if you're interested in using ZIO or contributing ZIO, I would encourage you to check out the ZIO organization on GitHub, which has ZIO core, and increasingly there's Kafka connectors and a whole bunch of stuff is forming around ZIO, a whole ecosystem is forming around ZIO. So I encourage you to check that out. And there's also a chat room that I frequent myself. Kai's on there, lots of people are on there, lots of ZIO contributors, and we're always trying to help people overcome whatever problems they have. So hop on to Gitter at ZIO core and ask any questions that you might have. And then there's a website which is currently not working, but it will be working soon, and it will contain the current microsite, which until then you can access on ZIO microsite or on the GitHub page for ZIO. And then you can follow myself on Twitter and Kai on Twitter and Pavel, who also works at Septimal Mind. You can follow all of us on Twitter. I hope you've enjoyed today's presentation. I certainly enjoyed being here. This is my first time in Ireland. I'm happy to be here. I had some good Irish stew last night at a local pub place. It was awesome, and I look forward to hanging out tonight. Unfortunately, I have to rush back. Yeah?
I have to say thanks to Paul Shershov, and thank you to all ZIO contributors who made this possible and really assembled a lot of hype, and thank you all.
Thank you, Kai. All right, well, that's it. Any questions before we wrap up today? Yeah.
Speaking of this? Or first. So if you're using the R type as a kind of replacement for dependency injection, I guess, like that makes everything visible at that scope. So all your dependencies are visible at that point in the code.
Yeah.
If you don't want that, if you want to hide some dependencies lower down, what's the technique you would use? And when would you use which technique?
Right, so the R type can be used not so much for dependency injection per se, because dependency injection has two components, the threading component, which you can use reader monads to do, and also the wiring up, which is a problem not solved by ZIO, but is solved by libraries like DStage, also developed by Septimal Minds, and libraries like MacWire and so forth. There's a lot of libraries out there to do that. That said, there's two ways to approach that. If you want to use ZIO, you can basically, in your implementation of a given interface that you're providing through the R type, in your implementation, you can depend on other implementations, and that totally hides them. So for example, if your database depends on some sort of HTTP connection library, you can hide that implementation detail and not reflect it in the type, because it is an implementation detail and should not be reflected in the type. The other way that you can do things like that is a ZIO effect can be considered as an arrow from one point to another. It's an arrow from R into A. And what this allows you to do is you can form a dependency graph using these arrows, and you can there's a method called provide sum on ZIO that allows you to eliminate some arrows but not others. So what that allows you to do is basically you express all these effects in terms of these other ones, and then you eliminate all these by specifying their expression in terms of these other ones. And that allows you to hide parts of the graph that aren't relevant to the current part of the application. So I recommend the first technique to start with because it's simpler and it solves the major problem that people have when they start with R, which is how do we hide the fact that this thing here depends on this thing here. We don't want client code to know or to have access to this thing over here. It's an implementation detail. So first technique solves that well. When you run into the limitations of that approach, and you're like, well, there's a flat layer. Well, of course, use DStage. But also consider modeling the dependencies in your graph as actual arrows and eliminating portions of them by expressing them in terms of other ones using provide sum. And then Pavel.
In case you need real DI for a large scale up. In case you need a real DI for a large scale up, you may try our library, which works great with ZIO, and it's non-invasive. It would work well with any kind of your beloved FP libraries, whatever. And we hope that one day we will measure it and contribute into the ZIO project.
Yeah, the interesting thing about dstage as a dependency injection tool is that it can handle tagless final and type classes and type class instances and inject all of that stuff in a way that can be verified at compile time. So it's really interesting. And keep in mind too that you don't have to use R. R is very convenient to use for a lot of cases. You can even use it to provide instances of tagless final type classes. So tagless final also has basically the same limitations as R in the sense that it's flat unless you do map K or something, eliminating dependencies in terms of other things. So they have the same, basically roughly the same set of capabilities. You can still do tagless final if you want with ZIO, and in fact it's a better tagless final because using the reader environment you can provide direct instances for almost any tagless final type class directly on ZIO, without using the local implicit hack that's often used in the functional programming community. Good question. Any other questions? Oh. All right.
Do you know if there's any plans to do a HTTP library that'd be ZIO native, so to speak?
A ZIO native HTTP library. Well, a lot of people use HTTP4S with ZIO, so it works very well with ZIO. Now you still have HTTP4S uses a Kleisli T, an option T, on top of the effect monad, so there's a lot of stacks, and that results in a lot of performance overhead. It'd be very interesting, I think, to explore more, either taking HTTP4S and translating it into a tagless final version that can benefit from ZIO's increased performance. ZIO will be 20 times faster than that stack of monad transformers. Or it could be interesting to explore maybe a native method for doing that. And I know, isn't Septum Lines working on the...
Using HTTP4S with ZIO.
Yeah, so a lot of people are... Yeah, a lot of people are doing that. So if you're already using HTTP4S, I mean, unfortunately, you're not gonna be able to eliminate the overhead of the Kleisli T and option T and other stuff inside HTTP4S by using ZIO, not yet. But if at some point they convert it over to tagless final for all that stuff, then you'd be able to power that by ZIO. And then, yeah, Kai?
Well, FS2 is in the process of migrating to tagless final right now. Like with the next major version of FS2, we may get some large performance gains from removing the huge free monad in favor of direct interpretation.
Yeah, that'd be fantastic. And then I know that some of my work with some of the Scala developers at Scalac involves not necessarily HTTP, but more remote procedure call, of which HTTP would be one target, so something more like Finagle, but in the ZIO ecosystem. And that could be interesting, I think, for folks when we get that out of the door. All right, do you have any other questions while you have the mic? No? All right. Well, thank you all for coming, and I hope you stick around. I think there's going to be pizza. Yeah, say hello. I'd love to chat and get to know what you're doing in the FP ecosystem. All right, thank you. Thank you, Kai.